Okay, everybody, so topic of this video, increasing and decreasing functions, which I am starting by trying to think about something really simple, okay? So see if you can share my train of thought for a second. So in order to tell you what an increasing or a decreasing function is, or what that would mean, I thought I would start and tell you, well, just look at this function. That function's fairly simple. And it would be easy for me to just do some calculations and let you see some numbers, okay? All right, so for this function, here's a table of values from -1 to 8 for x. And I just wanted to see if you notice a pattern about it. And I'd say, oh, there's definitely a pattern if you look. It looks like from here up to 4, the numbers are getting smaller, right? Okay, 28, 19, 12, 7, 4, 3, but from 4 afterwards, they're getting bigger. So that's a pretty simple pattern. And that's all we mean by increasing and decreasing. So the words mean just what you think they mean. So we would say let's say, well, here's the pattern we notice. That, like right in here, it's decreasing. And that's not really a complicated mathematical idea. I mean, these numbers are getting smaller. It's just a brute fact. And then from here onward, they're getting bigger. Okay? All right. Okay, so that's what we'll say about it. I hope that makes the concept simple. All right, so it's just a pattern with the numbers getting smaller or bigger. The y-coordinates specifically, right? It's not the x-coordinates, it's the y-coordinates I'm talking about, all right? Now, if you wanted to visualize this, then you might think of it something like this, all right? If I had this graph for this handy, then it would be a parabola. All right, it would look something like that. And this, like, bottom point of the curve, where it transitions from getting point by point smaller to point by point bigger, is right here at 4, okay? That's where the transition occurs. It's decreasing or increasing. You could also say, like, if you visualize it, that the curve is falling. Just look at it. 28, 19, 12, 7, 3, and then it picks up and it's rising from there. 4, 7, 12, 19. So we could say visually the curve is rising and falling, or the function is increasing and decreasing. We could just talk about that interchangeably. All right, so there's both the picture and the table, and you can take away from that whatever you like, okay? Now it's time for the math, and when you read the mathematical statements, it always seems more complicated than it is, I think. But here's the way that we might say it. Here's how calculus comes in. A function is increasing if its derivative is greater than 0. And a function is decreasing if its derivative is less than 0. So my function up there was increasing from 4 to infinity. So here's 4, and on the x-axis, infinity is out there. And it's like going to be rising like from 4 to forever. All right? And we would say that, what about the curve? What's the slope of the curve? Like anywhere in there. Anywhere. What's the slope of the curve? Going upwards. Well, what do we say if the slope of a line that's going up from left to right? We say it's positive. So the derivative is going to be greater than 0 from 4 to infinity. Okay? It's rising. It's increasing. And what about from negative infinity to 4? Well, so along the x-axis, negative infinity is out there somewhere. And this part of the curve, the slope is going down to the right. It's falling. There are lots of ways to say it, but we would just say f prime x was less than 0. Okay, so you've got a lot of associations to make. You look at the numbers. You got the concepts of decreasing and increasing of the numbers. The curve, that translates to rising and falling. Calculus, derivatives, and so on. That translates to the derivative's positive everywhere a curve's increasing, and it's negative everywhere it's decreasing. Okay, so let's go through like an example start to finish then. Okay, so here's like the way that we might see questions as they're presented to us. It might say something like this: find the open intervals on which the function is increasing or decreasing, and there's the function. Okay, so the way that we'll ultimately figure that out is not normally by making a table. I just started that way so you could get the idea. But the way that we'll do it is find the critical numbers and then test the derivative outside of or in between the critical numbers to see if it's positive or negative. Remember, if the derivative is positive, that translates to rising or increasing. If the derivative is negative, it translates to falling or decreasing. So, okay, find the critical. Well, what are critical numbers? Those are points on the curve where the derivative is either 0 or the derivative is undefined. That's what we mean by a critical number. All right. So, well, to find the critical numbers, obviously that involves finding the derivative. So, in this one, that shouldn't be too bad. So, f prime x is going to be 6x minus 4. Okay? And this derivative will never be undefined. 6 times the number minus 4 will always have an answer. That's always defined. It's never undefined. But this other case of the derivative being 0, that is a possibility. So I set it equal to 0. And I get something that's pretty easy to solve. I move the 4 over. And I get x is 4 over 6. Better said as 2/3. Okay? So there's my critical number, 2/3. Now the claim is that that's the place where the derivative is 0. The derivative is either positive or negative everywhere else. So think about my first example. I mean, if you have to visualize, then do that. Right here at the bottom, the derivative is 0. Everywhere else, it's either rising or falling. So you just need this critical number as a jumping off point. So what I'll do here on this next part is I'll just make a table. Okay? And I'll call this this table test points. And what am I testing? Well, I want to know if it's increasing or decreasing. I want to figure out where, and that would give me a glimpse into the shape of this curve. So what I'm testing is the derivative being negative versus positive. And I already know where the derivative is 0. So the only other thing to look for is positive or negative. All right? So the test points are going to be for the derivative. Okay? Derivative being 6x minus 4. Okay. So that's what I'm testing. I kind of ran together, but I'm testing the derivative. Now I already know that at 2/3, the derivative is 0. I just have to test one point outside or in between the critical numbers. So I just need one point out here, less than 2/3, and one point out here, more than 2/3. Okay? It doesn't matter which point. One point will tell you the whole story. So what's less than 2/3? Oh, 0 is a nice easy number. And what's more than 2/3? 1, that's an easy number. You can use any number to test. So, all right, so 0. What is 6 times 0 minus 4? That's negative 4. That's less than 0. And 1, what's 6 times 1 minus 4? That's 2. That's greater than 0. Okay? All right. Now, so that gives us this vision of the curve. All right? So imagine that you were looking at a graph and you were describing what you saw. Here's the x-axis, and here's what the derivative does. At 2/3, the derivative is 0. More than 2/3, like this number right here, the derivative is positive. In less than 2/3, the derivative is negative, okay? So this gives me the shape of the curve right here. It's falling, and then it's flat, and then it's rising, okay? Oh, so in other words, it looks something like that. You say, well, of course, it's a parabola. Of course it looks like that, okay? All right, so that's the test points. Can give me a look at this chart, and then I know where it's increasing and decreasing, okay? It's decreasing from negative infinity to 2/3. It's increasing from 2/3 to infinity because it looks like that. All right, now it's one more thing. Like when I tested this number to come up with that right there, I could have used any other number. I mean, the curve's falling. It has a negative slope no matter where you look. So I could have used 0, -1. I could use some weird decimals slightly less than 2/3. Just pick a number over here and over here to test it. Pick a number, one number. That's all you need. So let's give our answer like so, because we'll need like a formal statement of our answer. I had test points, I put them on a chart, and I made an inference about the shape and so on. But in the problem it says find the intervals on which the function is increasing or decreasing. So it's increasing on, that would be this, 2/3 to infinity. Okay? All right? And then it's decreasing on, that would be this right here. That would be negative infinity to 2/3. Okay, those are intervals. This is a portion of the x-axis that the curve is rising and falling. All right, so there's our first example with the procedure outlined for how we get intervals that the curve is rising and falling. It'll divide in 2 steps. Find the critical numbers and then test outside of or in between the critical numbers. All right, let's do one that with the math being a little bit more involved. Okay, that'd be this one. All right, now with this function, the domain is limited. Okay, so first I'll need to make a brief statement about that. Okay, so the domain, like, can you put just any number in for x in that? You can't, I mean, if you're going to get a square root being undefined, then that's no good for a graph, for increasing and decreasing and so on. So what numbers would cause that to be negative? Well, 4 squared 16. And if anything bigger than 4 is squared, 16 minus that will be negative. For example, 5 squared is 25. 16 minus 25, -9. Negative 5 squared, also 25. -9 again. So the domain is -4 to 4. This curve does not exist outside of that window on the x-axis, okay? Now, I know I didn't go into like a very detailed procedure about how you find the domain, but I wanted to at least get you, since this is calculus, not algebra, to tell you why. Well, you can't go bigger than 4 and you can't go smaller than -4. It doesn't work in that, okay? All right, so I want to find the open intervals within the domain where the curve exists, where the function is increasing or decreasing. Okay, so I got my steps outlined. So my first step was that I'll find the critical numbers. Okay, and that will involve finding the derivative. So I'll get y prime here. And so what's the derivative of x times root 16 minus x squared? I'll get root 16 minus x squared by the product rule, plus 1/2 16 minus x squared, -1/2 -2x times x. So that's what our rules for derivatives. Bring the power there as a half. Bring here, take away 1, Derivative of the inside is negative 2x. Then to complete the product rule, x. All right, that's the product rule derivative. That will be, let's do this. We'll say root 16 minus x squared. This here, let's cancel the 2 and leave the negative behind. And I'll get x squared like so over root 16 minus x squared. Okay. So, critical numbers. What was that? That's places where the derivative is undefined or 0. Within the domain, this derivative is not undefined anywhere, except for at the endpoints. Not in the middle, though. Okay, so the only critical numbers that we're going to get, I mean, the undefined case is not going to happen. The 0 case will. So here, critical number, can the derivative be equal to 0? Can we solve that? Here's how we can solve that. Say we take this term and move it to the right. Okay, then we're going to get like so. And say we take this and we multiply like this. Okay, what do we get then? Well, root 16 minus x squared times root 16 minus x squared is 16 minus x squared. And that will leave me this behind. Okay, rearrange a little bit. 2x squared is 16. X squared is 8. So x is either plus or minus 2 root 2. Okay. All right. So I got 2 critical numbers. Now, I won't say anything else about that because I'm going to incorporate it into my next step. So my second step, in order to find where the function is increasing and decreasing, that's ultimately a property of the derivative. Remember what I said when I started this? I said increasing means the derivative is positive. Decreasing means it's negative. So my second step is really just to test the derivative outside of and in between those two numbers. So I'll get my test points, which I'll put on this table right here. Okay. So here's x, here's f prime x. Okay, I'm going to test the derivative. What I know so far is at negative 2 root 2. Then the derivative is 0. And I also know that at positive 2 root 2, the derivative is 0. What I don't know is whether it's positive or negative outside of or in between these two values. Okay? If you want to accompany this with a chart, then it's like at negative 2 root 2 on the x-axis, I know the derivative is 0. And at positive 2 root 2 on the x-axis, I know the derivative is 0. Everywhere else, it's either rising or falling. Okay? The zeros just mean it flattens out and possibly turns around. So let's do so numbers outside of and in between. 2 root 2, that's a little less than 3. So let's do negative 3. We can't go further than negative 4, all right? Because that's outside their domain. And then let's do 0, and then let's do 3, okay? So now at this point, you get your calculator out. You put the numbers into the derivative. Where's the derivative? Well, right here. You see that formula? There it is. You put your numbers in there. And this is what you should get. For negative 3, you'll get about negative 0.76. Well, that's negative. So anywhere out here, the derivative will be negative because that one test point indicated is negative. And then when you put 0 in, you'll get 4. All right? And 4 is greater than 0. So anywhere in here, not just at that number, not just at that point, but anywhere is positive. And at 3, you'll also get negative 0.76. So negative. All right. So that's the shape of my curve. My curve is falling. It turns around. It rises. It turns around again. It falls. All right. So, you know, it's like just a crude sketch. Something like this. All right. On our interval. Something like that. Falling, rising, falling. That's what this tells me. That derivative tells me if the curve is rising or falling. So let's say this. Because our question, you know, I think I know what the curve looks like. It looks a lot like that. But we are asked to give intervals where the curve is increasing or decreasing. Let's say increasing on the interval -2 root 2 to 2 root 2 on the x-axis, and decreasing on, well, it's like -infinity to there. That's where it's falling. Okay? Oh, not -infinity. What am I saying? The domain's negative. The curve only exists here. It doesn't exist out left of -4 or right of 4. So I need to say -4 to -2 root 2. And also 2 root 2 to 4. All right. And then that would encapsulate all of the information. All right. Okay, same procedure. Much more detailed math though, right? Definitely more detailed math this time. But I did the same thing, and that's all I want to show you when I do all the examples is that I can like outline a procedure for you and just do different examples where the math might be more or less intricate, okay? All right, so let's go on to the next topic. So there is something called the first derivative test. And that is how we find relative maximum and minimums on a curve. It's how we, just to say it in rough terms, that's how we find the high points and the low points on a curve. Maybe you can see how that happens. I mean, I can read you the whole test, but you'll probably get lost in the details. So I might say this, like, look, this curve was falling, and then rising, and then falling. And that tells me it has a shape something like this. Wouldn't you think that if a curve transitioned from falling to rising, it must be that there's a minimum point down there. And if a curve transitioned from rising to falling, it must be that there's a maximum point in there. All right, now I think like that's just basic intuition about geometry. All right, but I wanted to tell you that way. So, well, that's what the first derivative, that's all the first derivative test says. If the derivative changes from positive to negative, what's that mean? Rising to falling? So think, rising to falling, there must be a maximum at point C. If like C is where the transition occurs. And if f prime changes from negative to positive, what's that mean? Falling to rising. Think of that shape, falling to rising. There must be a relative minimum. Well, of course, like, you know, all I'm saying is that in this first case, we're looking at something like this. Well, yeah, of course, there's a maximum. Rising, falling. And then here, falling to rising. There must be a minimum. Well, because that's what it looks like. So I hope this doesn't sound like something that's way out there. It's really not complicated, okay? All right, if you want to visualize something, you can look at that. F prime is positive. That means the curve's increasing. That means it's rising. If across that point, it changes to negative or decreasing or falling, then there's this relative maximum point. And vice versa, if it falls and right, you get the same thing I already said, but if you want to see it in that picture, this is a generic picture where you can see what it's like, okay? All right, now let's see if we can do one of those from scratch. So take this curve here. Can you tell me the critical numbers can you tell me where it's increasing and decreasing? And if you can do that, can you tell me where it has a relative maximum and minimum point? All right. Okay, so that's what that one's about. Let's do all of our math down here, and I'll put my answers up there. So for the critical numbers, that would involve the derivative. So I'll find the derivative of that, which is negative 21x squared plus 21. Okay. This will never be undefined by way of finding a critical number, but it could be 0. Okay. So I'll find my critical number by solving this equation. All right. So if I move the 21 over, I'll get that. And so I'll get critical numbers at 1 and negative 1. Okay. What do you square to get 1? 1 and negative 1. Okay. All right. So there are my critical numbers. Let me put that up here. X equals 1 or negative 1. Okay. Now, how, using the critical numbers, will we find where the curve is increasing or decreasing? Well, so that's something we talked about with the other examples that we were just doing. We used our test points. Okay, so we have a table, and I'm testing what? The derivative, being negative 21 x squared plus 21. I'm testing the derivative in between and outside of my critical numbers. So at negative 1, for example, the derivative is 0. That's what we found here. And at 1, the derivative is also 0. Outside of those and in between them, the derivative will be something besides 0, which means it'll be positive or negative. You can just take convenient number. What could we test less than negative 1? I don't know. How about negative 2? Why not? What could we test between negative 1 and 1? How about 0? And what could we test bigger than 1? How about 2? All right. Now I'll do the math. I'll complete the table, but I'm going to pause it while I do that. All right, and that's how the table looks. Okay. So what does that tell us? Let's put, in the other examples, I made the table, and then I made like what I'm calling a chart right here. But this is what we would describe seeing if we scan the x-axis. Say we were looking at this actual curve, and we say, oh, here's what I see. I see it rises and falls. This is how. So I have negative 1 out here. I have 1 here. And I'll describe what the derivative is doing. At negative 1, the curve is flat. At 1, the curve is flat. Left of negative 1, the curve is falling because I tested the derivative and it is negative out there left of negative 1. In between negative 1 and 1, the curve is rising because I tested it in between there and I got a positive number. It doesn't matter that I got 21. It just matters that 21 is greater than 0. It didn't matter what number I got. It's just that I saw that I got a positive number. It's rising throughout that interval then. And then over here, I got that it was falling again. Now, so there's my intervals where it's increasing and decreasing. Let's do this. It's increasing from negative 1 to 1. Okay? And when I say that, I'm not saying that's a point. X is negative 1, y to negative 1. That's an interval. I'm saying that this part of the x-axis is the part of the x-axis where the curve is seen to be rising. Okay, it's decreasing or falling, well, from negative infinity to negative 1. Okay. And also in this other portion, 1 to infinity. Okay, this curve has a domain of negative infinity to infinity. So from 1 out to infinity, from here on to forever, it's also decreasing. All right, I got that. Now, do you see how we can use all this to find the relative maximum and minimum points? This tells me the shape right here. Just think about it. Could that tell me the shape? You've got a curve that's falling, rising, and falling. Something like that. All right. That is definitely enough information to find the relative maximum and minimum points. If it transitions from falling to rising, that means there's a minimum right there. The point on that curve where there's a minimum has an x-coordinate of -1. So I'm going to say -1, and then I got to figure out the y-coordinate. The maximum, it transitions from rising to falling right there. That's where the maximum occurs. The x-coordinate of that point is 1. Okay? So it's going to look like this. What's the y-coordinate? I don't know yet. Okay? All right, now, how do we find the y-coordinates of the points? Do we use the derivative or do we use the original equation for the curve? Well, when I ask for the maximum and minimum points, I'm saying that, there's this curve and it has this shape to it, and there's a point that's up like that, and another point that's down like that. So those points are points on this curve. This is how you find the y-coordinate. What you'll get when you do that is that you'll find the y-coordinate of this one is 20. And if you put -1 into that, you'll find that the y-coordinate is -8. Okay? All right, so there's my relative maximum. And then here's my relative minimum. But make note that the way I found the y-coordinates was from the equation of the curve that I started with. This is the curve. That is the graph. This is how you get the points on it. And I'm saying these are points on it. Okay, so just make note to yourself, because for some of this we use the derivative, and for some of it we use the original. The derivative tells you if it's rising and falling, and tells you the overall shape. But the original equation, of course, tells you the points that are actually on the graph, and that's what we're looking for here. Okay, so there's all my information that I can find about this curve through the lesson. And I can make a rough inference of what it looks like too. Okay, this is what I think you'd see if you graphed it, something a lot like that. All right, so let's do maybe like 2 more to round this out. All right, so let's do this one, and yeah, I think then one more that I've got planned. When I wrote out this slide, I forgot to put step 1 critical number, so I'm going to put, that's not supposed to be an I or something. That's step 0, 1, 2, 3, 4. Okay, so I want to do that same procedure, building up to finding the maximum and minimum points on the curve. All right, let's start with the critical numbers. All right, that would involve finding the derivative. Okay, and of x to the 1/5 power plus 4, then that derivative is going to be 1/5 x to the minus 4/5. Okay, and so that is going to be, let's just do 1/5x to the 4/5 power, like that. Okay, all right, so what are critical numbers? Critical numbers are points where the derivative is either 0, is that possible? Or the derivative is undefined. Okay, now if that's the derivative, that will never be 0. I mean, if that is a constant, 1 divided by, or that constant divided by any other number is not going to be 0. Okay, so a constant over a variable can never be 0. Impossible. So this one does not happen. Can it be undefined? Well, 0 to the 4/5 power is 0. And so, yes, it can be undefined, divided by 0. So my critical number is x is equal to 0, where the derivative is undefined in that case. All right, so my critical number is x is equal to 0. All right, so now we'll figure out where it's increasing or decreasing on. So I just test outside of that number. right? So let's do this. Let's see, here we'll do some test points in an effort to follow up that first part. So my test points right here. Well, I know I've said it in the other examples. What am I testing? Test points for f prime. Okay, so I'll say x here, f prime, 1 over 5, x to the 4/5. Okay. All right, and 0, my derivative is undefined. Remember, because it was a critical number, and I need to test something outside of that. What would be easy to test in there? I think -1, actually, that would be pretty easy. And on the other side, I think 1 would be easy. Okay. And in case you're having, some calculators give problems doing that. So let me tell you when I get this number, how I do this. So x to the 4/5 power is the 5th root of x to the 4th power. You know, in subsequent steps, the power 4 over 5 is the 5th root of the number, and then once that's done, take that result, raise it to the 4th power. That's the root on the x, and then that's the power. Okay, so for -1, what's the 5th root of -1? It's -1. -1 to the 5th power is -1. What's -1 to the 4th power? It's 1, so you're going to get 1/5 right there. Okay, 1/5 is positive. And what if you put 1 in? You'll also get 1/5. That's also positive. All right, so here's what my curve looks like. I'm going to summarize my information on the chart. Here's the x-axis. Here is the derivative. It is negative. At 0, it's undefined. And for positive, it's positive. I don't know why I put that. For 0, it's undefined. And then to the right of 0 is positive. The curve's rising everywhere. What happens here? How could a curve be like rising and then have a slope undefined and then rising again? Okay. Well, it's because of this. It's rising. In a very early video I made, I talked about all the ways where a curve could be undefined. And one of them was if the curve was vertical. That's the only case that fits this. How could it be rising and then rising again? Because that transition there is vertical. Okay? All right. That's why the slope at 0 was undefined, because it's vertical, it turns out. All right, now, okay, so I think I've got what I need. It's increasing on -infinity to 0 and 0 to infinity. Okay. It's increasing, in other words, everywhere. It's decreasing nowhere. Does it have a relative maximum or minimum? Well, think about it. If the curve looks like that, does it have a relative maximum or minimum? Well, what did we say has to happen for there to be a relative maximum or minimum? The curve has to transition from rising to falling to have a relative maximum. And the curve has to transition from falling to rising to have a minimum. Well, if the curve here is rising everywhere, you know, if that's just the nature of its shape, then it cannot have a maximum or minimum point. It can't have this, and it can't have that anywhere. All right? So relative maximum, there isn't one. The curve does not have the right kind of shape to have a relative maximum. And relative minimum doesn't have one either. The curve does not have the right kind of shape to have a relative minimum. It just doesn't. If it's rising everywhere, it doesn't have the right kind of shape. That's what we can tell from this. All right, so there's everything about this one. One fine detail about it is it's vertical there at the point where the derivative is undefined. The derivative is undefined because there's no way to measure the slope of a vertical line. And there's a point right in there where the curve is vertical. All right, so let's do, let's see, I have to make a decision. Now let's do this one, okay? All right. So, yeah, that one's it's different enough. I think if we do this one, that will round it all out. That could be the last one that we need to see. So this time, 2x plus 1 over x, all right? But same list of questions. Start with the critical numbers. So f prime. That's how we find our critical numbers. All right, f prime x, that's going to be 2 minus 1 over x squared. Okay. All right. So this is undefined at 0, it turns out. Okay. But that's just because we have a vertical asymptote there. You know, right here, that's not continuous at 0. So there's like a gap in the graph. Okay. So like here, like the curve shoots up to infinity and negative infinity around the 0. So it's just discontinuous. It's not like the curve is vertical there, that it has a corner or something like that. Okay, so let's say that we don't need to worry about where the derivative is undefined. Where is the derivative? 0. Okay, so I'll set equal to 0. And then I'll get like so. Okay, and then get like so, and then plus or minus, let's say 1 over root 2. Okay. Maybe this will be rationalized, and to me it does not really matter if you rationalize it, but you know, you could give this number or that number. Okay. All right. No big deal. I think I'll probably just use that one, but either way. So there's my critical numbers. There's 2 of them, okay? So I get 1 over root 2 or negative 1 over root 2. 2 critical numbers. Okay. You could also write that one, though. But I'll just go ahead and use these. Increasing and decreasing. Well, that one involved testing the derivative. So let's do test points. For what? For the derivative, right? As I've been emphasizing for, I think, the entire video. But anyway, all right, so here's my table. There's x, and I need to test the derivative. F prime x being 2 minus 1 over x squared. So far, I know that at negative 1 over root 2, the derivative is 0. And at positive 1 over root 2. The derivative is 0. Okay. Now, I need to test some numbers outside of and in between that. That number right there is about 0.7, I think. Yeah, I should know that. It's 0.7. Whoops. Okay. 1 divided by root 2. I just feel like I should demonstrate that. So 0.7, yeah, so 0.7. So I might, how about this? Let's do negative 1 less than, that's negative 0.7. Let's do 0, and let's do 1. Those would be pretty easy numbers to test. Okay. If I put in negative 1, I'm going to get 2 minus 1. So that's 1. That's greater than 0. If I put in 0, okay, I'm going to get 2. Okay. Or sorry, oh, it's undefined. I didn't mean to put 0. That's where it has its asymptote. So let's do negative 0.7. I'll do negative 0.5. Okay, so that's in there. And let's see, that's a half squared, that's a fourth, so that's going to be negative. So 1/2, 1/4, 2 minus 4, negative 2, less than 0. And then for 1, I'll get 2 minus 1. And that's also going to be 1. That's going to be positive. Okay. So I have enough to test it, everywhere. So let's look at our table. So here's f prime versus x. And here's my critical numbers. Negative 1 over root 2, 1 over root 2. And I found out that it's plus here, 0 and 0 here and there. It has an asymptote in the middle, right? It's not continuous at 0. It has a vertical asymptote. But I can tell from negative 0.5 or positive 0.5, I'm going to get the same result. The derivative is negative, so it's going to be falling in there. And then to the right of that, I got 1, that's positive. So it's going to be rising, falling, falling, right. So I'm going to get a maximum here and a minimum there. Now, I know that the graph of this one would be harder to visualize than the others that I've showed you. I mean, I'm not saying it's the hardest graph in the world, but compared to the other ones I've showed you. But it's still like our principle is that rising, transitioning to falling means there must be a maximum where that transition, where it turns around, all right? And that's what I'm going to see here and there. Okay. So anyway, let's do this. It's going to be increasing here and there. So let's say this, increasing on negative infinity to negative 1 over root 2. And also 1 over root 2 to infinity. Okay? All right. Decreasing from negative 1 over root 2 to root 2. Okay, so like that. And that. What about relative maximum and minimum? Well, this describes the shape of the curve. Okay, so let's leave it like this. Right there, that will be a maximum. So we'll say the maximum is going to be at negative 1 over root 2. That's going to be the x-coordinate of the maximum. And then the minimum is going to be right here. That's going to be the y-coordinate. Or sorry, that's going to be the x-coordinate of the minimum. Okay? So 1 over root 2. All right, how do we get the y-coordinates? Well, we put the x-coordinates into this. All right? So for both of these, I'm going to get y, because these are actual points on the curve, this way. Okay? All right. So anyway, let me pause it, do the math there, and tell you what I get. All right, so that's the numbers that we get. All right, for the relative minimum and the relative maximum. I'll elaborate a little bit, maybe with that one, how I came up with that number. So say I put this in for x, I'll get 2 times 1 over root 2 plus 1 over root 2. Okay? This will be 2 over root 2 plus root 2. If I add these by getting a common denominator of root 2, this is going to look like 2 over root 2 plus 2 over root 2. If I multiply top and bottom of this one, considering it's over 1, by square root of 2, that's what I get. So I get 4 over root 2, which I suppose counts for that number. But if you rationalize this, you're going to get 4 root 2 over 2, which is just 2 root 2. Okay, that's how I got that number. Okay, so one final thing about this example right here. I know really getting to the point where you're probably like, enough already. There's something I should emphasize a little bit before we just put this one away. Here's the actual graph, okay? It has critical numbers, negative 1 over root 2, 1 over root 2, and technically 0. When I was doing this, I didn't emphasize that one because then I thought that basically it wasn't going to be where the minimum or maximum occurred. All right. But technically, it is not continuous there. The derivative is undefined at 0 because it's got this vertical asymptote at 0. But for those or these, I'm saying that the curve is falling and rising. That's a minimum, a local minimum, okay? And this is rising to falling. That's a local maximum or relative maximum, okay? But still, across that, okay, across 0, it is falling and falling on both sides, all right? And I really would need to test both of those, but it's falling everywhere in there. So one more thing, I mean, like I said, I know it's probably enough already, but 0 is, like, technically it's a critical number. It's not one that leads to a local or relative max or min, but let's put, like, there's a vertical asymptote at 0. And it's falling on either side of that, okay? All right, so yes, falling here, falling there. It's going downward in each case. But that's what the actual graph looks like. I thought it'd be nice for this one to elaborate a little bit more about it, as that being a kind of a nuanced detail about it. Anyway, but there's my final answer for all the specs for it, and that's what the actual graph looks like.